My name is Soyoungju, and this is my team, Team 혜움나래, representing Korean Music Leadership Academy. And members are Sangchul, Doyeon, Seungchan, and Dongyeong. So briefly before we start, I just want to mention one thing. So I know at the end of the day, we have this, since this is a physics fight, we have a winner and a loser. However, let us not forget that we all are winners in this competition because we all learned something from this competition. And wherever you go, and even in this competition, let us not forget that we always have to keep in mind the fundamental question, which is physics. Thank you.
Okay, the opponent team.
Hello, ladies and gentlemen, and to the professors who I really respect, and to all the audiences. It's a great honor to be here to present in front of you. The team name is Team Mighty. And the reason our team name is Mighty is because previous year our school's team name was Joker, and Mighty is better than Joker. So our team name is Mighty, and today I want to introduce our teammates. First, my name is Jaewon. The team leader is Woo Yeon-song, Ha Kyung-kim, Young Jae-jang, and Hoon Kim. Today, I want to enjoy this game and learn more about physics. Thank you very much.
Then the reviewer team.
Hello, this is Team Format from Hana Academy Seoul. It's such a great honor to debate with all these ace teams and in front of honorable judges. Our team, my name is Kim Ji-yeon, the team captain, and from my right, Kim Gon-young, Park Hun-jun, Jung Ji-yeon, Lee Jun-un. I hope you could have a very fruitful physics fight today. Thank you.
And the final team, the observer team.
Good morning, ladies and gentlemen, and honorable judges and the audiences. My name is Jae-kook from Hanyang Community High School from Team Coach Thomas, and we are the first time in the finals, and the name of my team members are Kim Jae-hyun, Cha Sung-won, Lee Ji-yeon, and I wish you guys enjoy our fights. Thank you.
Okay, and I'm sorry about the lack of mics, but I guess I'll ask each of the judges to introduce themselves.
My name is Hong Jung from Korean Women's University.
My name is Chan Bok Lee from Gyeonggi National University. Chan Soo-ji from Gangwon National University. Nice to see you.
I'm Hyun-woo Lee from Hanseong University. Sang-seok from Gangwon University.
I'm James Jo from Hannam University.
I'm Lee Sang-yan from Yeongwon University.
I'm Young Boy from University of India.
And I'm Yoon Daniel Park from Seoul National University, so we'll get started with the first physics fight. Unlike the preliminary rounds, I believe all the teams have decided on their problems to present and oppose. So I guess we'll give 5 minutes to the opponent team to get ready. And if you don't need all the 5 minutes, please let us know so we can get started.
일단 자리에서 할까요? 네. 자리에서 큰 소리로 한번 해볼게요. 시간 얘기도 제가 큰 소리로 해볼게요. 마이크 왔다 갔다 하면 시간이 걸릴
Hello, ladies and gentlemen. My name is Songchul Lee from Korea Min족 Leadership Academy, and I'm here to present the problem number 9 of the test of KYPT, the rocking bottle. So the problem statement suggests a situation in which there is a cylindrical bottle filled with some liquid, and then pushed along a horizontal surface. So let's see the problem is to investigate the motion of the bottle. Let's see the full chart of my overall presentation. First, I'll show you the observation of the phenomenon, and then I'll move on to the theoretical modeling of my rocking bottle, and then I'll move on to the experiment part of my presentation, and combining all the experimental results and theoretical expectation, I'll move on to the conclusion of my presentation. So let's observe the actual phenomenon of rocking bottle. As you can see in the video, as the bottle is rolling along a horizontal surface, the liquid inside the bottle is oscillating back and forth. So you can see that the surface of the liquid is actually tilted to one side. So, in order to get a decent grasp of the motion of the bottle, I made this experimental setting with adjustable slant and cylindrical bottle. And yet, the problem statement says that the bottle should be given a push. But I used the adjustable slant because using slant shows almost the same phenomenon of rocking bottle, and yet it is more easier to control the initial condition of the experiment. So this is the actual velocity graph of the rocking bottle. So you can see here that the velocity is oscillating. So it is increasing and decreasing repeatedly. And from my observation, I noticed that at the maximum and minimum value of velocity, the surface of the liquid inside the bottle is actually almost horizontal. And the bottle accelerates and decelerates when the liquid is tilted to one side. So at first, intuitively, I thought that the motion of the liquid inside is simple harmonic motion compared to the pendulum. And for that assumption, I concluded that the motion of the bottle will also be the simple harmonic motion. Ladies and gentlemen, this is the graph of the acceleration of the bottle. What you can see here is that there's this odd two-peaked shape at the maximum and minimum value of the acceleration. This means that the motion of the bottle is not simple harmonic motion. So I needed to make a new theoretical model for this rocking bottle phenomenon. So let me move on to the second part of my presentation, theoretical modeling. So the most important factor of my theoretical modeling is rigid body assumption, that I assume that the water inside the bottle is rigid body. But how can I prove this? How can I give a ground for this assumption? So I added the glycerin powder inside the liquid and observed the phenomenon again. What I observed by the movement of the glycerin powder is that there was not much turbulent flow or vortex. It means that the angular velocity of every part of the liquid was almost consistent, which will be proved for the rigid body assumption. And as I assumed the liquid is a rigid body, I could have the center of the mass and or the forces, gravitational force, normal force, frictional force acting on the liquid, and the reaction of the forces and other frictional force acting on the bottle. So I'll move on to the point. So the next point is the non-inertial reference frame. In order to interpret the motion of the liquid inside, I have to set the reference frame at the center of the bottle. However, there exists the reaction of the frictional force and normal force, and the frictional force between the bottle and the horizontal surface, which will make the bottle accelerate. So defining the theta as the angle between the vertical line and the center of the mass. I can get the first equation by adding all the horizontal component of forces. And by adding all the torque acting on the bottle, I can get the second equation. And by combining two equations with the smooth rolling condition, which I could observe in the phenomenon, I could express the acceleration of the bottle in terms of the normal force and frictional force. The next factor of my theoretical modeling is the friction. But there exists the friction between the liquid and the bottle. What should be the frictional force? So, should it be the frictional force between the solid and solid, as I assume the liquid is rigid body? But applying this friction to my model cannot expect the experimental result when the characteristic of the liquid is changing. So here I apply the shear stress between the solid and liquid, in which there is a two solid plate and thickness D filled with liquid. As the upper plate is trying to move, there will be frictional force. Then another question appears here, that what should be the thickness D? For that, my answer is that there will be an imaginary plane that will act like the moving upper plate in the rocking bottle phenomenon. And then I again observed the phenomenon with the glycerin powder. And I gave the relative velocity to the bottle and the liquid. And as you can see, over here, the motion of the glycerin powder is comparatively stationary comparing to the motion of the glycerin powder near the radius. So, by measuring the thickness of the imaginary line, I could get the thickness of 1.1 millimeter. So, next I'll move on to the motion of the liquid. So there will be normal force, gravitational force, frictional force, and inertial force, as I said, the reference frame at the center of the bottle. And I can get the first equation by adding on all the torque acting on the liquid. And I can get the second equation by adding on all the components of centrifugal force. And solving this equation, I could finally express the acceleration of the bottle in terms of the motion of the liquid. And then I calculated the motion of the liquid using Oxford mathematical program. And this is the theoretical value of the acceleration of the bottle. And you can see that my theoretical model can actually predict the two-peak edge at the maximum and minimum values. However, there's some discrepancy between the experimental value and theoretical value. And I believe this is to other sources of bonding friction and resistance and limit of measurement, and I do not get the really specific value of the initial angle of the liquid. So in my equation, I found some parameters I could change in my experiment. The radius of the bottle, and the mass of the liquid, which can be controlled by the volume ratio, and the friction force, which can be controlled by changing the viscosity. So let's move on to the third part of my presentation, my experimental results. So as I said, these three values as a parameter, I could get this acceleration amplitude, period, and damping factor as a significant factor that can show the experimental results. So the first parameter was the volume of the liquid inside. And as a factor, I used the acceleration of amplitude. And as you can see in the graph, the theoretical value and experimental value is very consistent when the volume ratio is under 50%. However, surprisingly, there is a huge discrepancy when the volume ratio is actually over 50%. So explanation for this discrepancy is following. So the center of the mass, when the volume ratio is low, is almost is very away from the center of the angular motion, which will lead to the consistent angular velocity at every part of the liquid, which fits with the rigid body assumption. However, as the volume ratio increases, the center of the mass reaches to the center of the angular motion, and the rigid body model assumption predicts that the angular velocity will be consistent at all parts of the liquid. The actual phenomenon shows that the direction of the motion at the upper part, when the volume ratio is over 50%, is actually the negative direction, and is not. Due to this, the rigid body assumption does not hold anymore when the volume ratio is over 50%. So I conducted additional experiments to confirm that my solid body model fits when the volume ratio is under 50%. The second parameter of my experiment was the radius of the bottle. So as I solved the motion of the liquid as a solid, rigid body, my solution fairly fits with the physical pendulum. So the increase in the radius of the bottle will be expected to result in the increase in the period of the oscillatory motion. So this is the second experimental result. As you can see here, as the bottle radius is increasing, the period of oscillation is actually increasing. And for the third experiment, I set the parameters of the viscosity of the fluid. So increasing the viscosity of the fluid can increase the frictional force, and I defined the damping factor as the ratio between the first oscillation and second oscillation to show how fast the damping occurs. And this is the experimental result for the third experiment. And as you can see here, as the viscosity is increasing, the damping factors, both theoretically and experimentally, is decreasing. However, there's some discrepancy in this graph because there can be other sources of the frictional force, and increasing viscosity can actually result in the more confirmation of the rigid body model. So in conclusion, a rigid body model is valid when the volume is under 50%. And when the volume is under 50%, the rigid body model could effectively predict the experimental result when the parameters were volume of the liquid, radius of the bottle, and viscosity of the liquid. Thank you very much.
Okay, the opponent team, please take some moments to ask questions to the reporter team.
Hello, my name is Jaewon, and thank you for your reporting. And I have several questions to ask to you. First of all, can I know the direction of the friction you said in your model?
Yeah.
The direction of the friction in your model. Can you show your model, please? What is the rocking ball rotating? The direction of the rotation?
Sorry for the inconvenience that I did not note the actual velocity, but the direction of the friction is the negative of the direction of the angular velocity.
The angular velocity is turning like this. Rocking ball is turning like this at that.
No, I interpreted the motion of the liquid, the oscillator motion, as a pendulum motion.
And can you show me the experimental setup for each experiment?
The experiment setup. So my basic experiment setup uses an adjustable slant and models with different radius.
Okay, thank you very much. And do you think that the pushing effect and the adjustable slant, the initial motion is same? Does the result is same?
So your question is that whether pushing and using the slant has same effect. But what we need to see here is that both pushing and using slant makes the inertial force as the bottle is accelerating, whether you push or roll it down the slant. And due to that inertial force, there makes an imaginary gravitation. And to the direction of the imaginary gravitation, the water surface will tilt. So this tilted water surface is the main factor that makes the oscillation of the liquid inside.
Okay. Thank you very much. Reporter team, please take a couple of moments to prepare.